Jai Hind to all. Myself Richa, Assistant Professor in Ajay Kumar Garg Engineering College. Today we will discuss about the microwave measurement of part 2. It means the remaining part of your microwave measurement from the previous lecture we will discuss today. So first is we will discuss about measurement of dielectric constant. Basically in the microwave microwave system we are using a particular type of the dielectric. Through this dielectric the measurement and all the functions of radiation can be find out. So electromagnetic property of a non-magnetic material or medium can be completely specified by its either its permeability, conductivity and the dielectric constant. So today we will concentrate on the measurement of this dielectric constant. So first we will discuss about all the three property of a medium. First is the permeability, that is mu. Mu of a medium is a measure of the efficiency of the transfer of magnetic force. It means how efficient your the medium to transfer a magnetic force. Next is the conductivity. Conductivity sigma is the measure of the efficiency of transmission of the electric charge. It means how efficient your medium is for the transmission of the electric charge. Last one is the dielectric constant epsilon. It is a measure of efficiency of transfers of the electric force. So basically a particular dielectric, or we can say particular medium, is responsible for the transfer of the magnetic force, electric charge and the electric force. So today we will discuss a particular medium is how efficient it is to transfer a electric force. So dielectric constant is basically a complex term which has a real and the imaginary part, and it is given as epsilon is equal to epsilon naught into epsilon prime minus j epsilon double prime, and where epsilon naught is the dielectric constant in a free space, epsilon prime is the ability of a dielectric to store energy, and epsilon double prime is a measure of dissipation of energy in the medium. So dielectric constant also referred to as a permittivity of a medium, that can be written as epsilon is equal to epsilon r into epsilon naught, where epsilon r is the relative permittivity and its relative permittivity is given by epsilon naught, and it is equal to epsilon prime minus j epsilon double prime. So we can solve it as we can take epsilon prime outside the bracket 1 minus j 10 sigma. So what is this? This is the loss tangent of your dielectric medium. So loss tangent is defined as epsilon double prime upon epsilon. See here, when we are taking the epsilon outside the bracket, we get 1 minus j epsilon double prime minus epsilon prime, right? So this factor is loss tangent. So we can write it as a loss tangent. So this is the experiment setup of a dielectric constant calculation. It means how we can calculate the dielectric constant. See, this is the microwave test bench, and this test bench, first is your microwave source, and here the source we are using one padding, or we can say we are placing an isolator here. After that the frequency meter is used to find out the frequency of the signal which is traveling through your system. After that slotted line, and through slotted line we have connected a detector, crystal detector, and the output of this crystal detector is measured at the SWR meter. In this we have put one dielectric sample here and the short circuit. In this setup, first we are taking the reading without this dielectric sample, and we will measure what are the first two minima on the SWR meter. After that we will connect a dielectric sample again and find out what are the first two minima. So the shift between these two minima basically give us the value of the dielectric constant. So see, the guided wavelength is measured using the frequency meter. From the frequency meter we can find out the frequency, and from the formula of the relation between the frequency and the wavelength we can find out the guided wavelength. It means what is the wavelength which is traveling through the waveguide, that is called the guided wavelength. Now the thickness of the dielectric which we want to measure, we measure the thickness of this dielectric with the help of a micrometer. It means from the micrometer device we can find out the dimension or thickness of the dielectric which we want to measure. Now the micrometer of a short circuit, for example, we have taken one reading it here. Now the same thickness we are using in a short circuit. So micrometer of a short circuit is then adjusted to read the same value as the thickness of the dielectric, right? So the value of short circuit will be same as the value of dielectric. Now exact position of first and second minima from the right hand side of the VSWR meter we will not. It means first we will calculate what is the position of first minima, then what is the position of the second minima. After that, short circuit is then removed and the dielectric sample is inserted into the aperture of the short circuit, and without moving the short circuit plunge. It means we are not moving any device, any position of anything in the circuit, and we will place or insert a dielectric sample which we want to measure. Now this dielectric field short circuit on the SWR detector is then replaced, and the position of first minima and second minima we will again measure. So the shift in the position of first and second minima, which is denoted by delta S of the standing wave caused by the dielectric, is determined. It means which is the shift is given by delta S, and this is the measure of the dielectric constant. And if the dielectric thickness is D, okay, from the here, if the dielectric thickness we are using it here, thickness is D, right? So we will calculate the quantity X. What is that quantity X? X is the lambda G by D. What is lambda G here? Lambda G is the guided wavelength, 10 of 2 pi del S plus D upon lambda G. So in this formula we know all the things, and this delta S is calculated from the experimental setup. Lambda G we know what is the guided wavelength which is traveling through the waveguide, and right. So this is the factor X. Now one famous researcher Robert and von Heppel have developed a plot X versus V. It means this factor X versus voltage, right? So they have given a graph between X and V for calculating the dielectric constant, okay, by relating X to another quantity V using the relation. So they have given one graph between X and V. If we can calculate the value of X, so corresponding V can be calculated, and the relation between X and V are X is equal to 10 of 2 pi V upon V. And what is V here? V is the number of wavelength of the microwave radiation in the distance D of the dielectric field guide. So see here, this is the graph given by the researcher, and here the value of X, and this is the value of basically the relation between X and V, and this is 10 of 2 pi V upon V. If we know the value of X from our experimental setup, because from the experimental setup we are getting the value of delta S, and by using the value of delta S we can calculate the value of X, and from this graph according to the value of X we can calculate the value of V, right? So from these two values how can we calculate the value of your dielectric constant? Okay, so the value of X measured, value of V are read from the plot, and the dielectric constant is a measure using this formula. See here, epsilon R is equal to 1 minus lambda naught by lambda G square plus lambda naught by V D by 2. So all these terms in this equation we know. So from these we can calculate the value of epsilon R. This is your dielectric constant which we want to measure. So this above procedure is repeated at a different frequency, and the value of dielectric constant ERS is determined. What is that ERS? This is the average of these gives the dielectric. It means we can take a number of measurement from the setup, and after that we can take out the average of all the dielectric constant to find out more accurate and value of your dielectric constant. So second measurement is the measurement of S parameter. In any device, if we want to study any device, so we have to know what are the S parameter of that device. Scattering parameter are the parameter through which we can find out the your device characteristics, right? So the scattering parameter can be measured by two methods. One is the network analyzer, and second one is the measuring the amplitude and phase from the port through the dual directional coupler. So first we will study about the measurement of S parameter using network analyzer, then measurement of amplitude and phase through dual directional coupler. So how the S parameter can be calculated using network analyzer? Network analyzer are of two types. One is the scalar network analyzer and second one is the vector network analyzer. So scalar network analyzer provide only magnitude characteristic of microwave device as a function of frequency, right? So from here we can only find out the magnitude of the characteristic. But in the vector network analyzer, it is the complex reflection and the transmission characteristics of microwave device. It means through from the vector network analyzer we can find out magnitude as well as phase of the characteristic of any microwave device. So in a network analyzer, the basic principle of the measurement is to generate an accurate reference signal basically, and the comparison between the reference signal with the test signal whose amplitude and phase we have to measure. So it means first we will generate a test signal, and this test signal will be compared with the reference signal, and according to the difference between these two we can find out the amplitude and phase of the signal. So see, this is the setup of network analyzer. Here one sweep generator is used to generate a signal, and it is given to the power divider, or we can say the power splitter. It will split your signal into two parts. One is the test signal which is given to the device under test, and second one is the reference signal which is given to the length equalizer basically. Now the signal of these two will be compared and given to the harmonic frequency converter, which will convert your signal into one IF frequency, and from this IF frequency we can find out amplitude and phase of the test signal. So a sweep generator feeds a power divider or splitter that convert it into the two signals. One is the test signal and second one is the reference signal. The device under test is fed with the test signal, right? So the device which we want to measure is given the test signal, and the length equalizer takes in the reference signal. These test and the reference signals are then converted into a standard IF frequency by harmonic frequency converter. The output of a harmonic frequency converter is then used to determine the amplitude and phase of the test signal, and from which then S parameter can be calculated. See here. So from the amplitude and phase we can find out the S parameter. Measurement of S parameter by the second method, that is the dual directional coupler. So this is your dual directional coupler. Here the first we will use it in the first direction from 1 to 2, then the reference and load will be interchanged. So S parameter of a two port network can be obtained by measuring the amplitude and phase from the ports from the dual directional coupler by interchanging the RF signal from the load position. See here, this is the dual directional coupler. RF signal is given it at this point, and from this it is given to your DUT, then again dual directional coupler to the load. This is the first case. In the second case, see, this load is placed it here and RF signal is placed here. It means the position of the load and RF signals are interchanged. So after getting the phase and amplitude from the directional coupler as well as from the network analyzer, your S11 will be calculated as V2 upon V1 phi 2 minus phi 1, right? When your first figure, when RF input is at this side and load is at this side. S21 is the V3 upon V1 phi 3 minus phi 1, right? By measuring S22 and S12, the RF signal and loads are interchanged. Okay, now load is placed it here and RF signal is placed here. So we can calculate S22. S22 is V3 upon V4 phi 3 minus phi 4. S12 is equal to V2 upon V4 phi 2 minus phi 4. Basically, S11 is nothing that the input given at port 1, how much is reflected from port 1, come back to port 1, right? So S22 is the input is given at to port 2 and how much is reflected back to port 2. Basically, this is the reflection from the port. Next is the measurement of the noise factor. Basically, the noise factor is defined as the ratio of actual output noise power of the device to the noise power that would be available if the device were perfect without itself contributing any noise. It means that the ratio of the device under test by the ratio of the device when it is completely ideal input. So noise figure F is the noise factor expressed in the decibel. The unit of a noise figure is in a decibel, and it can be written as 10 log 10 input signal to the noise ratio upon output signal to the noise ratio. How it can be measured? This is the measurement setup of a noise factor. Here we have used one noise source, padding, then device under test and the power meter. So initially the noise output from the device under test is noted, connecting its input to the mass termination, right? After that, the input of the device is connected to a standard noise source using a pad. See here, this is the device under test. It is connected with the under test is connected with the mass termination, right? And after that, input is given with the one noise source. In between there is some padding. Now this pad is adjusted until the noise output of the device is double. So when we have done this setup, we are getting one noise factor, right? Now this will be adjusted to get the double noise power. So the noise factor, or we can say the noise figure of the device, is then equal to that of the noise output from the attenuator, right? So next measurement is the return loss measurement. How return loss can be calculated from your microwave test bench. Return loss is basically known as the reflection loss, and it is a measure of fraction of the power that is not delivered by the source to a load. It means if we are transmitting any signal and if there is mismatch from the transmission line impedance with the load impedance, then your signal will be reflected. So this reflection is basically a loss. So how much how fraction of your input power is reflected back is basically the return loss, or you can say how much power is not delivered to the load is the reflection loss. If the power incident of a load is Pi, if we are considering that we are giving input power as a Pi and the power which is reflected by the load is the PR, then the return loss in decibel can be expressed as 10 log Pi by PR. It means the ratio of input power by your reflected power with 10 log. It means why this is 10 log, because we have represented it with the inner decibel. The better the load is matched to the source, the lower the, it means if your load is perfectly matched, then there will be no reflection, and if your reflection is no, it means PR will be 0, then return loss will be 0. It means all the signals which is transmitted will be 100% delivered to the load. So the return loss or we can say reflected power, hence the higher the return loss. Return loss is positive quantity if the reflected power is less than the incident power. See here, if this factor is very small, right? Small, it means 0 point something. So this complete unit will become very large. So overall your return loss will be high. And if your reflected power is 0, so something divided by 0 will be infinity. So your return loss is very high, right? Less than, if the load has a complex reflection coefficient rho, then your return loss will be 10 log 1 upon rho square, or we can say 20 log rho. That is, the return loss is negative of the input reflection coefficient expressed in decibel. So how we can use this negative in the decimal? So we can use like this. So when generalized to a terminated 2-port, this is your 2-port device, port number 1 and port number 2. The return loss is defined with respect to input reflection coefficient to the terminated 2-port. So this is source here, this is your input reflection coefficient, rho in, input reflection coefficient. The 2-port in figure has the input reflection coefficient and it is written as S11 plus reflection coefficient S12, S21, 1 minus reflection coefficient S22, right. So this symbol is used for reflection coefficient. This is the for if we have used subscript at L, it means this is the reflection coefficient of load L, it means here. So this is your reflection coefficient at load. So return loss of a terminated 2-port is minus 20 log mod of reflection coefficient and input. Okay, so this complete factor, take the mode of this, after that multiply it with 20, take out the log of this factor and multiply with minus 20. So complete formula will be minus 20 log S mod of S11 plus reflection coefficient of load S12, S21, 1 minus reflection coefficient of load and S22. So if your load is completely matched, if load is matched, it means your ZL is equal to Z naught. What is that Z naught? That is the system reference impedance. It means the impedance at which you want to match with the load. So see here, if your ZL and Z naught are same, so this factor will become 1 basically. So it comes out to be minus 20 log S11. This return loss is also called the input return loss, since the reflection coefficient is calculated at port 1, because we have calculated, see here, we have calculated reflection coefficient at port 1. The output return loss is calculated looking into port 2 in the reverse direction. We can get the values of S11, S21, S12, S22 from the scattering parameter and calculation as discussed in the previous lectures. This calculation can be done. Next measurement is the impedance measurement. So impedance at microwave frequency can be measured by any of the following 3 methods. First is the magic T, next is the slotted line, third one is the reflectometer. So from the magic T, it will explain with the magic T also how, what is the application of magic T. One of the application of magic T is the measurement of the impedance. So magic T is having 4 port. So see here, these are the 4 port number 1, 2, 3 and 4. At port number 1, standard variable known impedance we have used. At 4, null detector, port 3, microwave source, and at the port 4, unknown impedance, right. So as we know, as per the property of your magic T, these are the power at port number 1 by root 2 A3 P2, that is the rho 2, that is the reflection coefficient of Z2, right. So in this way all the reflection coefficients are written it here, and from this reflection coefficient what are the signal which is traveling at a particular 4 ports are given. So the net value reaching the null detector, what is the input to the null detector from port number 1 and port number, see here. So this is the null detector from port number 1 and port number 2. These two signals are reaching it here. One is the unknown impedance and one is the standard variable known impedance. We want the null detector should be at 0. So how it can be 0 if it is unknown? So we can vary the value of non variable impedance. So after varying this, we can find out the zero value at port number 4, or we can say the null detection. And at this point, at this null point, what is the value of this Z1 is the impedance of this unknown device. It is basically work like a bridge. Okay. So see here, net value reaching the null detector is 1 by root 2, 1 by root 2, A3 rho 1 minus 1 by root 2, 1 by root 2, A3 rho 2. So finally you can get out 1 by 2 A3 rho 1 minus rho 2. So the perfect balancing of this bridge, basically I have already said that it works like a bridge or null detector. We will equate it is equal to 0. When we are equating it is equal to 0, so this factor will be cancelled out. We can write that rho 1 minus rho 2 is equal to 0, or rho 1 is equal to rho 2. What is this rho 1? In terms of impedance, reflection coefficient in terms of impedance is written as, if I am writing Z1 minus ZZ upon Z1 plus ZZ, right? So at point 1, so it will be 1. Okay. So if we are taking the standard formula, so it can be Z0 minus ZL upon Z0 plus ZL. Z0 is the input impedance, Z0 is the characteristic impedance, and ZL is the load impedance. So here the characteristic impedance we have considered as Z1 for port 1, and load impedance is ZZ. So we are writing reflection coefficient in terms of impedance. So from here we are getting Z1 is equal to Z2. So thus the unknown impedance can be measured by adjusting the standard variable impedance till the bridge is balanced and both impedance become equal. So see here, from this equation what we have concluded? We have concluded that the value of Z1 and Z2 is same when your bridge is balanced, right? Practically what we have to do, practically when you have connected a unknown impedance, you are getting some value at the null detector, not the 0. So if you want to do it 0, you can vary your Z1 impedance, known variable impedance. When you will vary it, finally you are getting 0 at the null detector. At that point, what is the value of Z1 is equal to Z2. So the value of Z1 is the value of unknown impedance. Second method of measurement of impedance is the slotted line. So in this method, impedance is measured using slotted line and the load ZL, and by using Vx, Vmin can be calculated. In this method, the measurement of impedance takes place into the two steps. First, we will determine V minimum using load ZL. After that, V minimum by short circuiting the load. So see here, this is the first setup, impedance measurement using slotted line, microwave source, attenuator, slotted line, this is your unknown load, crystal detector and the power meter. Okay, when we have used the unknown load. Second setup, microwave source, attenuator, slotted line, crystal detector, power meter and shorted terminator, right? So we can measure the V minimum with unknown load, after that V minimum using shorted termination. So V minimum we can find out. So see here, so when we try to obtain the value of V max and V minimum using a load, we get certain value. However, if the same is done by short circuiting the load, minimum will get shifted either to left or the right. So we have to take one reference, either we can take it as Vmax or Vmin, right? So we will find out from this reference, either your waves are shifted to the left or right. Depending upon these two values, we can find out whether it is the inductive load or the your, we can say, capacitive load. If the shift is to left, it means the load is inductive. See, if the shift is left, it means the load is inductive in nature. And if your shift is in the right, it means the load is capacitive in nature. So by recording the data, unknown impedance is calculated. Basically from this method we can only find out what is the value of your what is the type of your impedance, whether it is inductive or the resistive. So impedance and reflection coefficient rho can be obtained in both magnitude and the phase. So from here we can find out the formula for rho in terms of magnitude and phase. So see here from the setup 1. Setup 1 we have calculated one waveform at your output device and we have taken this as a reference, right. So we can take any reference here, reference point we have taken it as V, minimize the reference. After that we have used setup 2. In the setup 2 now unknown load we have replaced and at the unknown load we have connected a short termination. So see here, now we are seeing what will happen. This V minimum is shifted towards this side, left side, and from the last slide it is written if it is towards the left it means load is inductive. See here, this V minima is shifted toward this point, it means this load is inductive in nature, right. And if your load is shifted towards right, see if this reference point is shifted it here, then your load will be capacitive. It means first we have to find out what is the reference at from which point we want to measure. Actual your complete waveform is shifted. See here, this complete waveform is shifted towards here, and if we are not taking any reference point, so we can find out this is your point and now it comes it here. So we can mislead it as this is the capacitive load. So first we have to mark what is your reference point, and from this reference point only you have to measure whether it is shifted to left or right. Next method of measurement of impedance is by using reflectometer. So unlike the slotted line, reflectometer helps to find out only the magnitude of the impedance and not the phase angle, right. So we can only find out what is the magnitude of your impedance. In this method, two directional couplers are identical but different directions are taken. It means both are placed in the different direction but both are identical. So two couplers are used in the sampling, the incident power Pi and the reflected power PR. So from both the directional coupler we will calculate what is Pi and what is the PR. The reflectometer is connected as we will show in the next slide, and it is used to obtain the magnitude of the reflection coefficient rho from which the impedance can be obtained. So see here, this is your reflectometer, right. So this is your microwave source, attenuator, forward directional coupler, and here reverse directional coupler and connected with the load. Both direction coupler are identical, but here we are using it in the forward direction and here we are using it into the reverse direction, right. And one load is connected. Pi is the input given it here and this is the PR which we want to measure. So see here, input to this direction coupler is the Pi, right. This Pi is given to the forward detector and finally it comes out to reflectometer, and here it is connected into the reverse direction. It means now the input is connected at this side and here input is the PR, what is the reflected power, and this reflected power is now going into the reverse directional coupler to the reverse detector and finally to the reflectometer. This will give the these are basically the 20 dB directional coupler. So these two values are coming into the reflectometer. Reflectometer basically give the ratio of reflected power to the incident power. So here we are getting two input, one is your PR and one is your PI, right. So reflectometer inside will do the calculation which is equal to under root of reflected power upon incident power, right. It is divided by 100 because of this is your 20 dB direction coupler. So this ratio will give the reflection coefficient, and from this reflection coefficient we can find out the impedance. How we can find out the impedance? See here, the relation of reflection coefficient with your impedance is Z0 minus ZL upon Z0 plus ZL, something like this, okay. So see here, From the reflectometer, we can find out the reading, that is PR by PI, right? So this reflection coefficient, from this value we can find out VSWR as well as the impedance, because this is the relationship between VSWR and the reflection coefficient. We know the value of reflection coefficient, so VSWR will be 1 plus reflection coefficient divided by 1 minus reflection coefficient. And if we want to find out the impedance, so this is the formula for impedance. Basically Z is your characteristic impedance here, and ZG, or this is a ZG is the unknown impedance which you want to measure, and some your standard formula for reflection coefficient is Z0 minus ZL upon Z0 plus ZL, right? L is the load impedance, and at the load side we have connected an unknown impedance, so we have used it as a ZG. So in the last we will discuss about 2 meters. First is your VSWR meter, second one is the power meter. So VSWR meter is the high gain, high Q, low noise voltage amplifier. Basically in this the input is given, this amplified input we are getting at a VSWR scaled meter. So it is tuned to a particular frequency at which the microwave signals is modulated. So VSWR meter use a detecting signal output of a microwave detector as its input. It will amplify the same and provide the output to a calibrated voltmeter, and this meter itself can be calibrated in terms of VSWR. So meter directly meter indirectly measure the degree of the mismatch between the transmission line and the load. So this is the different scale which we are getting at the VSWR meter. First scale is the voltage scale, which will give the value of your voltage from 0 to 10 millivolt. Then is the dB scale. After that VSWR scale, and this VSWR scale in the expanded VSWR scale and the expanded dB scale. So there are 3 scales: normal VSWR, expanded VSWR and dB scale. Normal, it means it is used between 1 to 4 to calculate the VSWR between 1 to 4, right? And for VSWR between 3 and 10 at the bottom, normal SWR can be calculated. Expanded scale, it is graduated from 1 to 1.3 and hence will be used with the VSWR less than 1.3 or an accurate reading. dB scale, this scale is used for measuring VSWR directly in dBs. Next is the power meter. Power meter is used to measure the power, and here we are using power sensor that will convert the microwave power into the heat energy, and this heat energy will give the current in a particular circuit, and from there we can calculate the power. It means the current will going into the low frequency circuit which will give directly the power. So temperature change provide an output current into the low frequency circuit that indicate power. And the sensor used for power measurement, we can use the barodiode, bolometer, thermocouple. All are the temperature sensitive device. According to the temperature, the resistance of the circuit is going to change. So the Schottky variate diode detector can be used to measure power level up to 70 dBm, which implies that it can measure only low microwave power which is less than 10 milliwatt. So this is all about your power meter. Last topic of the microwave unit 4 is the microwave amplifier. A microwave amplifier is a device for enhancing the output power signal to a microwave device, usually by increasing the amplitude or height of the wave that directly relate to its power level. It is accomplished by channeling additional input power to a microwave device so that its microwave radiation carries more energy. Such amplifiers are usually operated at low frequencies of the radio wave spectrum, which ranges around 30 megahertz or higher, and they are used for a variety of purposes, from broadband communication to radar system and electronic warfare by the military. Several different types of microwave amplifier exist, that are Gaitron, Klystron and the Amplitron, which is also known as the cross-field amplifier. So now we will discuss one of the numerical here. Calculate the SWR of a transmission system operating at 10 GHz, assume TE10 wave. Transmission inside a waveguide, dimensions are given, the distance between twice minimum. So here what is given, first is your F. So F is equal to 10 gigahertz. Next, assume that TE10 mode. So for TE10 mode, your lambda C is equal to twice of A, and A is given as 4 centimeter, right? After that, we can find out the lambda naught. Lambda naught is equal to C by F. So C is 3 into 10 to the power 8, and F is equal to 10 into 10 to the power 9. It comes out to be 3 centimeter. Take it into the centimeter. So it comes out to be 3 centimeter, right? Lambda naught we have calculated. So the relation of lambda G is equal to lambda naught upon 1 minus lambda naught upon lambda square. All values we have calculated. So it comes out to be around 3.24 centimeter, right? Now we have to calculate VSWR. So VSWR can be calculated lambda G upon pi D2 minus D1. Okay. In the last slide, what is given as D2 minus D1 is 1 mm. So after putting all the values, so lambda G 3.24 centimeter and 3.14 into 1 mm, right, or centimeter. So in meter we can calculate it as 10 to the power minus 1. So calculated it, so it comes out to be 10 gigahertz. Sorry, not in the gigahertz, it comes out to be 10 point something. Okay. So Jai Hind to all. Jai Hind to all. This is all about your microwave measurement unit 4. Thank you.